Okay, so here's an example of a problem that we would like to solve. We have a volumetric charge density contained within a volume V, and the volumetric charge density is rho sub V as usual. And at some point P, we are interested in finding some field quantity, such as the voltage at point P or the electric field at point P. So from what we've just seen, we know that Laplace's equation applies, and if we can solve this equation, given this volumetric charge density, rho sub V, we can find V, and from V we know that we can then find E by going backwards. So this is a challenging problem to solve, or more challenging to solve, because it is again a non-homogeneous differential equation. And it would be easier to solve if the right-hand side were zero. In fact, the right-hand side is zero in many parts of this problem. If I take this field point, or this observation point, and I move it outside V, so let's say I move it outside of this volume to this point shown here, then actually at that point, there is no volumetric charge density. So the right-hand side is zero, and we get the homogeneous equation that we're looking for. So that equation, where the right-hand side is zero, is called Laplace's equation. So it is a special case of Poisson's equation, and it holds everywhere outside the source region. So everywhere outside this volume V, our problem reduces to solving this homogeneous differential equation, and it basically turns into a boundary value problem. It's important to also realize that we can apply the same concept to many other charge distributions, not just volumetric charge distributions. So the same is true in turning Poisson's equation into Laplace's equation if we had a surface charge density or a line charge density, or even a discrete distribution of point charges, so long as our observation is not coincident with the charge density itself or the point charges in the case of a discrete distribution, we can turn the problem into solving Laplace's equation. And even with a combination of volumetric, surface, line, and discrete charge distributions, we can apply the same concept.
So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are two sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically outer space, from outside our solar system, and they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil. And so this emits ions which can be transported upwards, but they're typically trapped in the boundary layer. So they're stuck in the lowest kilometer of the atmosphere. So this charge is being generated all the time.
These equations look intimidating, but don't worry, we're not going to derive them. I'm only going to show you what they mean and what they imply in practical terms. And we're going to visualize them with graphics that I hope you'll find useful. Objects have something called a charge. This is a property of matter, like mass is a property of matter. In practical terms, what this means for large objects with negative charge is that it has more electrons than protons. The first thing I want you to visualize is that if you have a static object with a charge, it will affect only other charges. And if you have a static magnet, it will affect only other magnets. It will not affect charges. But if you have a moving charge, it will affect a magnet. And if you have a moving magnet, it will affect a charge. At the simplest level of description, that's what these four equations are telling us. It is best to think of this as a field, similar to the quantum fields of quantum field theory that I spoke about in another video. But for visualization, you can think of this as being similar to the gravitational field. The first equation is a formula that tells us how electrical charges create electrical fields. It's based on concepts developed by Carl Friedrich Gauss. It basically tells us that if you have an electrical charge, there will be an electrical field emanating from it. If you want to know the strength of this electrical field, you can calculate it using this equation. Note that the strength of this electrical field is proportional to a constant called epsilon naught. This is known as the vacuum permittivity. This is a property of the vacuum of space. It can be thought of as the resistance of free space against the formation of an electrical field. The second equation is referred to as Gauss's law for magnetism. It's the equivalent of the same equation for magnetism, but it's kind of a negative law. It basically says that if you have the same sphere, but instead of having a charge inside, it was a magnet, you'll never find a configuration where the magnetic lines of force always point outward or always point inward. There's always as much field pointed out as there is pointed in. It will be in loops. In other words, a magnet will always have two poles. There are no magnetic monopoles. You cannot have a positive magnet or north pole by itself or a south pole by itself. You might say, well, I can take this magnet and cut out the north pole. Wouldn't that create a monopole? No, you would just create a smaller magnet with two poles. You can keep cutting this in half over and over, and you would always have two poles. The third equation is called Faraday's law. This law basically says that if you move a magnet, you will create an electrical field. In other words, if you change the magnetic field with time, it creates an electrical field. What does it mean to create an electrical field? It just means that you put a charge there, it will be affected, it will be accelerated. This equation tells engineers how to generate electricity from a generator. You can take large magnets and rotate them, and if you put a wire near it, as you move the magnet, then electricity will be created in the wire. This is because there are electrical charges in the metal wire, and as electric field lines are created, these charges will move, creating a current of electricity. The fourth equation is Ampere's law. It basically says that if you have a moving charge through a wire or an electrical current, you generate a magnetic field. In other words, two wires can be attracted to each other if they have current flowing through it. The equation will tell you how strong the magnetic field would be. So if you have a given current flowing through a wire, let's say 1 amp, and you are 1 meter away, how strong would the magnetic field be at that point? This requires another constant of nature called mu naught. This is known as the permeability of free space. This can be thought of as the ability of free space to allow magnetic lines of force to go through it. Note that there are two terms in this equation. One term tells you that moving electrical charges can create magnetic fields, and the second term tells you that moving electrical fields can also create magnetic fields. This idea of magnetic fields being created from electrical fields was Maxwell's addition to Ampere's law. And he just thought it up in his head. It was not based on any experiment. He figured that there should be some symmetry with Faraday's law, because if moving magnets could create electric fields, then moving electrical fields should also create magnetic fields. Now I want you to take note of epsilon naught and mu naught. Both of these constants have to be measured, since they are inherent properties of nature. They are not derived from anything. You might say at this point, well, you're just talking about electricity and magnets. What does this have to do with light? So here comes the most interesting part. Let's take what we've gleaned from Maxwell's equations and now put it to practical use. Put yourself in Maxwell's shoes at this point. You're working with equations and concepts that other people really don't know about much in the early 1860s, and you are staring at them for a long time, trying to see some patterns here. And you are mathematically trying to figure out what these equations are telling you. So now you think to yourself, maybe I'll do a thought experiment. What if I take an electric charge and put it on a pole outside my house, and I just move it up and down, up and down? What will this cause? Well, if you did that, then according to Ampere's law, if an electric field moves or changes with time, it would create a magnetic field perpendicular to that. And because of the changing movement of up and down that you're making with the charge, the magnetic field will also be changing with time. And according to Faraday's law, the moving magnetic field would create another new set of electrical fields. Now, since the same thing is happening to these new electric field lines, that is, they're changing over time, they would in turn create new magnetic fields. And the new moving magnetic field would create yet more electrical field lines. So this becomes like an unstoppable positive feedback loop of electric fields creating magnetic fields, creating electrical fields, creating magnetic fields, and so on. Each is produced by the movement of the other. You have just created a self-propagating wave. This is analogous to throwing a rock in a lake. It disturbs the water, so the water starts to oscillate, and it pulls its neighboring molecules up. So the first wave will pull its neighboring molecules up, which oscillates more water, which moves more of the molecules from neighboring water. And this is the way a water wave propagates. So now you're Mr. Maxwell, and you're trying to figure out what kind of wave you've just created. This wave must be occurring in nature because electricity and magnetism exist. So you think about that, well, what would this wave look like? How fast is the wave moving? So you calculate using what you think the speed could be by manipulating the equations that you have. You do this by using advanced multivariable calculus, which Maxwell was exceptionally good at. We won't go through how it's done here, but what Maxwell comes up with is 1 over v squared is equal to epsilon naught times mu naught. And solving for velocity, you get that it's equal to the square root of 1 over epsilon naught times mu naught. So what the equations are saying is the velocity of this wave is inversely proportional to the permittivity and permeability of free space. Does this even make sense? Well, permittivity can be thought of, as I said earlier, as the resistance of free space against the formation of an electrical field. Think of this like viscosity. A more viscous fluid like molasses would be harder to swim through than water. You wouldn't swim very fast in molasses. Similarly, a wave flowing through a substance with lower permittivity would propagate faster. For free space, epsilon naught is equal to the following number. And permeability can be thought of as the resistance of a material against the formation of a magnetic field. And it's equal to this number. So it makes sense that the velocity of any wave would be inversely proportional to the resistance of the substance it's traveling in. You might at this point ask, well, why are mu naught and epsilon naught those exact values? That's a real good question. No one knows why. These are just the constants of nature. These are properties of free space that tell us how fast magnetic fields and electrical fields can interact with each other. If there's a finite speed at which the electrical and magnetic fields can interact with each other, then it sets a limit on how fast these fields can propagate through space. In a different substance or a different universe, these constants could be different. Now we take the measured values of these two constants and do some simple math. Lo and behold, what you find is that the wave you've just created is moving at about 300,000 kilometers per second. This is really fast. This would go all the way around the Earth almost 8 times, or close to the distance of the moon in 1 second. What kind of wave moves this fast? You're Maxwell, and you say to yourself, wait a minute. You remember that in 1728, English astronomer James Bradley had calculated what the speed of light is. It's about 297,000 kilometers per second. And a huge eureka moment hits him that light must really just be a manifestation of electricity and magnetism. It is an electromagnetic wave. Can you imagine how Maxwell's insight from this must have felt? There was a point in time when Maxwell was the only person in the world who realized this. Now, he could not prove it at the time, but about 20 years later, Heinrich Hertz proved experimentally that Maxwell was absolutely right. And the rest of the story is that about 40 years later, another great scientist by the name of Albert Einstein did his own thought experiments inspired by Maxwell's equations. And his thought experiment was based on one simple assumption. He asked himself, if the speed of light is an inherent property of space, why would the speed be any different based on the speed of the observer? It shouldn't matter whether you measured the speed of light moving on a fast train or whether you measured it standing still. It should be the same regardless of your reference frame. And it was from this simple assumption that he came up with the special theory of relativity in 1905, which changed our ideas about the nature of time. Later in his life, when people suggested to Einstein that he stood on the shoulders of Newton, he corrected them and said, no, I stand on the shoulders of James Clerk Maxwell. The man who inspired not only Einstein, but to a large extent is responsible for creating the equations used by every electrical engineer to create some of the most cherished and useful technologies that we use today is James Clerk Maxwell. And as the history guy likes to say, this is history worth remembering.
Magnetohydrodynamics, or MHD for short, is the study of the dynamics of electrically conducting fluids, which include plasmas, liquid metals, and salt water, in the presence of magnetic fields. The term itself combines three concepts. Magneto refers to magnetic fields, hydro means fluid, and dynamics indicates motion. So why is MHD important? MHD is crucial because it describes how magnetic fields interact with moving conductive fluids. First formulated in the early 20th century, the principles of MHD are used in a variety of fields, from astrophysics to engineering. In astrophysics, MHD helps explain phenomena such as solar flares, which are intense bursts of radiation caused by the movement of plasma in the sun's magnetic field. Understanding these processes is vital for predicting space weather that can impact satellites and power grids on Earth. In nuclear fusion research, MHD plays a critical role in the design and functioning of reactors like the tokamak. The containment and control of plasma within these reactors depend on understanding and applying MHD principles to maintain stability and achieve successful fusion reactions. One of the cornerstone equations in MHD is the combination of Navier-Stokes equations used to describe fluid motion, with Maxwell's equations which describe electromagnetism. This blend allows for predicting and analyzing how magnetic fields and fluids interact over time. The equations involved are extremely complex and often require sophisticated computational techniques to model and solve real-world problems. Researchers continue to develop advanced algorithms and simulations to better predict MHD behavior. Besides its scientific applications, MHD also finds its place in engineering solutions, such as developing advanced propulsion systems and energy conversion technologies that could revolutionize how we approach resource utilization. By understanding magnetohydrodynamics, we unlock deeper insights into both natural and engineered systems, paving the way for innovation and discovery. Like and subscribe for more videos like this.